So you see that that's the whole purpose was of the, like the table that we made was to show you that, things are actually the same. So basically we're going to solve this problem in a very similar manner. So before, how did we solve the expenditure minimization problem? We used it as, how do we solve any constraint minimization or maximization problem? We use the Lagrangian, right? So as you can guess, we're going to again use that. But if you check, for instance, if you check here, so how can we actually identify this point? What can we say about that point, right? So the optimal point, you said, the hocam, it should be the sort of this total cost line should be tangent to the isocont, right? That we would like to produce, whatever amount we would like to produce, it should be tangent. That's what we said. So what is the characteristic of this tangency point? It means that slope of total cost curve, right? Cost curve, this one, absolute value of the slope of the total cost curve is equal to the slope of the so the total cost slope in isocont, right? Slope of the isocont. Okay. Now, what is the slope of the isocont? We learned it's called marginal rate of technical substitution, right? So this is marginal rate of technical substitution. What is the slope of the total cost curve? We just figured out, right? So minus W over R, but it's the absolute value, wage over R. So you see the optimality condition is just as in the expenditure minimization, we had margin rate of substitution equals to Px over Py. Here we have margin rate of technical substitution should be equal to wage over R. Okay, so you see graphically, again, we have this, but in order to say that every point that satisfies this equation is the optimal point, what do we need? Remember we said in the consumer theory. Right, so we said convex indifference curves, right? In order to say this, so we said that when indifference curves are convex, that's what we said. Now here, when we have convex isoconts, which are coming from, convex indifference curves were coming from which utility function? I told you that we're going to use them forever. So they were at least, they have to, they come from at least quasi-concave utility function. Apparently, if I have these guys, right, convex isoconts, then they're coming from a production function, which is also quasi-concave, right? At least quasi-concave, that's what we said. So apparently, if your production function is quasi-concave, or if your isoconts are convex, right, then we said that this condition is not only necessary, but sufficient, right, to say that that point is the optimal, right? So that's what we said. But also, there was another thing we have to know in order to say that, the tangency point is the optimal point. We have to know that we have convex indifference curves or convex isoconts, and remember we said we had to have, this was actually one of your exam questions. We have to have an interior solution, right? Otherwise, if it's a corner solution, remember I solved it and I said that no, we cannot solve it like that, right? So if it's a corner solution, again, we cannot, right? So it's going to be, this condition is necessary and sufficient, right? When we have an interior solution and, when we have basically convex isoconts, okay? So this was the graphical one. Then you would say that, hocam, we know how to solve this, right? Mathematically. How are we solving this? The cost minimization, so the expenditure minimization problem. Now it's going to be the cost minimization problem. So let's say mathematically we can solve it like this, right? So our problem is minimize this total cost, wage times L, R times K, right? So L K, that's what we said. subject to f of lk equals to q0, right? Some level. That's why it's called conditional input demands, okay? From the solution of this problem is going to be called conditional input demands, okay? So this is going to be the case. So now we're going to set up the Lagrangian. How am I going to set the Lagrangian up? Right, so we said W times L, R plus K, R times K, plus lambda Q0 minus F of L K, okay? That's it. Now I'm going to start taking derivatives, right? So this is going to be the first one, del L over del L, right, with respect to L. So this is wage, as we know. If I take the derivative, what's going to be? Minus lambda, right? Minus lambda times del, right? So either f of L or del f over del L, right? Which is equal to 0. So the second one, del L over del K, R minus lambda times del f over del K, which is equal to 0. Okay? And then the third one, remember, the third one would always give when I take the derivative of the Lagrangian with respect to lambda, the constraint, right? So this is going to be Q0 minus f of Lk, which is equal to 0. Okay? So this we know. So we move on. Again, if you want to solve this, the typical like approach we use is that you said wage is equal to lambda times del f over del k, R is equal to lambda times del f over del L, del k, okay? So you just take the ratio of these guys go away, you have wage over L equals to del f over del L, del f over del k. What is this guy? Ratio of the marginal products is, so this is f of L, right? So this guy is f of L, this guy is f of k. This is the definition of, right? So we show that it's equal to the marginal rate of technical substitution. This is exactly what we have figured out there, right? So mathematically we can also have the same result, right? So this is basically the case. So what about lambda? How can I remember in the consumer theory, how did we call lambda? Lambda was what? Do you remember? Lambda was the marginal utility of income. It was the marginal utility of income. Now let's try to see what it means here, okay? So let's see. Marginal, so let's see what is lambda. So in order to interpret lambda, and again, if you want to interpret, remember this equation, so we missed your grandma, so I haven't been, mentioning her recently. So now if you want to explain this condition to your grandma, either coming from the graphical explanation or coming from the constraint optimization, solving the constraint optimization problem, what can you say? How are you explaining this to your grandma? Px over py. This was what? Your value. Right, so you said that this is how much you value, right? You're willing to, in order to have one more x, how much y you're willing to give up, right? And this was the market's value, right? And in the optimal point, we know that they should be equal to each other. So here we said that it's very similar. This is the rate at which the firm is willing to, in order to have one more labor to produce the same amount of output, how much capital they're willing to give up. And this is basically, how much market values, okay? One input for another, okay? So basically, this is the rate at which market is willing to trade one input for another. This is the rate at which you're willing to trade one input for another, okay? So if you want to interpret it to your grandma, you can say it like that because she wouldn't know what is MRTS, right? Or these expressions, okay? But now, what about lambda? What about lambda here? So what is lambda? So let me check lambda. Lambda is what? Lambda is basically wage over, right? Del L. So if I put this here, wage over del F over del L, okay? Or R over del F over del K, okay? So this is actually what we said. Lambda is this. So let's think of lambda. If I hire one labor, let's say 1 hour of labor or 1 unit of labor, whatever, okay? How much money I'm going to pay? If I hire an additional labor, how much money I'm going to pay? W, right? Wage. Now, that one guy, how much will he contribute? How much additional output he's going to produce? Right? So del F over del L, right? So this is the definition, remember, of marginal product. I hire one more labor. What is his contribution to the total output? Or you can call it F of L, right? So apparently I am going to pay this guy this much money, but he's going to bring me this much output, right? This much output, del F over del L. So for 1 unit of extra output, how much money I paid? Wage over, right? This. Suppose this guy is going to bring me 5 extra units. And suppose wage is 10. So then 1 extra unit of output cost me 2, right? So basically you see that this ratio, and you can say the same thing about capital. So you see that this, we can write it as, so you can interpret lambda here as marginal cost of producing an additional unit of output. Okay? So you understood the logic, right? So if I have one more labor, I'm going to pay him wage. So that one more labor is going to bring me this much extra output. So for 1 unit of extra output, I'm paying this much. Okay? So this is how you can interpret lambda, marginal cost of producing an additional unit of output. Okay? So basically, this is the case. And then we wrote down the problem, and then we said that we're getting those conditional input demands. Okay? Now, fine. So these stuff that we have known. So suppose I would like to, let's say, produce more. Suppose I want to expand as a firm. Okay? So let's see. So how are we, remember in the utility maximization or expenditure minimization in the consumer theory, how did we call this part? Wage over R. What were we getting from here? Del F over del L, del F over del K. In the expenditure minimization or utility maximization, remember the this first order conditions from them were the same, right? So what were we getting from the first 2 equations? It was called income expansion path, right? So basically it was telling me that when I expand, right? So when my income increases, right? How would my optimal points change, right? Sort of, it was giving me that, right? It was giving me all those optimal combinations of X and Y, good X and good Y, right? Now, let's try to think of it here in again a similar context. So I'm going to K, I'm going to put L here. It doesn't matter whether it's, you know, like utility maximization or expenditure minimization that we have seen. So suppose I have, if I want to produce this much, suppose, right, Q is equal to Q0. We said that, oh, this is the optimal amount of capital and this is the optimal amount of labor if I want to produce, okay? Suppose I have this. Suppose I want to produce more. I want to, as Toyota, I would like to expand, okay? I want to produce a higher unit of output. Then, again, cost minimization tells me, okay, whatever output you would like to produce, I know your optimal, right, capital, and given the wage and R, I know your optimal amount of optimal capital and labor, right? So what is the slope of this line? Right, minus W over R, right? Then suppose the wage over R, they don't change, but I want to produce more. Then, of course, my costs will be higher, right? So let's say I'm here. So my new optimal point would be here. What is the slope of this line? Right, the same, minus wage over R. That's what you said. And then, so hocam, this new optimal point is here, okay? So then if I keep on doing this, suppose I would like to produce more. I'm Toyota. I want to, like grow. I want to expand. So let's say Q2. Of course, I should write Q0 is less than Q1, Q2. Okay, otherwise it wouldn't mean. And then, as usual, my y-axis is always too short, right? So it's basically, so then I actually, so this is, you can call this, let's put this. So for instance here, it's LC, let's say, prime. So KC prime, okay? So let's put this. And then here, as we said, that hocam, the new optimal point. Okay, I'll cheat. So again, you said the hocam, the slope is minus wage over R here. This is going to be the optimal point, right? So this is basically the case. So let me call this KC double prime, okay? And let me call this LC, this guy here, LC double prime, okay? Now, so this is basically the case. Now, if I connect all these points, all these optimal points here, this is called, guess what? There's no income. It's literally expansion path, okay? So this is called expansion path. Okay, if Toyota would like to expand, these are all the optimal amounts of, if Toyota would like to produce this much, this is the optimal amount of capital and labor they should be using, right? Çok yaşa. So, right, so it's actually the amount that they should be using. If they would like to produce this much, this is the optimal amount of capital and labor in order to produce Q1 level of output, right? So this is basically, this is called the expansion path, and then we know how to get it, right? When you solve the problem, you would get the expansion path from here. K is equal to something L, right? So that's what we said. Now, so this is the expansion path. This is actually the question that was in your exam, and you'll see it's very similar here. So how do I know? Remember, we know things about the income expansion path. Whatever we learned, the links, they would also be valid here. So in which cases this expansion path would be a ray through the origin, would be a line, right? When it is going to be linear. So the expansion path would be like this. One, or we said homothetic, right? So when the function, exactly, remember when the utility function was homothetic, we said that the income expansion path was the ray going through the origin. It was a line, right? It was linear. So here, similar thing, when production function is homothetic, then your your expansion path, right, would be a ray going through the origin. Okay, so now, fine, this is the case. But here, I could have actually drawn this in this way. Suppose instead of this, I had this. So it goes like this. So I'm going to draw this again. Hopefully, I'll be successful. But suppose I have something like this. Okay, so suppose I would like to produce this much, okay? And then Okay, so this is minus wage over R. And suppose the optimal point is here. Okay, you see, it depends on these curvature of these isocons, right? Or in the utility theory, in the consumer theory, indifference curves, right? Suppose the optimal point is here. So let's say, okay, I cheat a bit. Suppose this point falls a little bit here, okay? Instead of this guy. Then what's happening here? How does my expansion path look like? Suppose my LC double prime is here. Okay, so this is KC double prime, but my LC double prime is here. How is my expansion path? It goes like this, right? And then from here, apparently it's maybe, and if I look at other points, it goes like this. Instead of going like this, it's actually going backwards, right? So remember your exam question, then do you think that, what's happening here? So when Toyota would like to expand, apparently they are using, at some point they would like to use the optimal amount of labor they would like to use is decreasing, right? So you see that when you want to grow from here to here, you see, how would we call, if this was a good, we would call it an inferior. Then you can call labor an inferior input, okay? So this is, for instance, an example to this would be the following. Suppose, and you know that it's very popular in our country, suppose you're a construction firm, okay? So suppose you are making small houses and not of great scale, right? Then you might be, in order to make more houses, you might be hiring, right, more labor. But suppose now you become Alaoğlu, right? You would like to have all these, you know, ugly buildings. And then, so now after, you know, if you want to grow after a certain point, do you think you can hire more labor or you need cranes? You know what crane is? Winch. Okay, so you need cranes, right? You need like bigger, or you might think of it, if you want, you can think of these as flats, right? So it's like if you want to build houses of, you know, like 1 or 2, 3, right? So if you want to grow, you can hire more labor, right? But if you want to, you know, like build houses of, you know, like, I don't know, like 50 or, 60 flats, then basically you might need, in order, when you grow, you might even decrease your, labors, and you might want to have more capital, okay? So this is, in that case, for instance, you might think that for construction, at some point, labor might be an inferior input, okay? But by the time, of course, you might tell me that, hocam, but labor, there's also the engineer there, right? Not only the workers who are working in the construction, but you have also the engineers and such. That's why we have those assumptions which you don't like, probably. Not every labor is the same, right? You have engineers and you have unskilled people who are doing literally the construction, right? So, or you have someone, a crane operator, right? Vinç operatörü var, who's actually using the crane, right? So you see that those homogeneity assumptions, they're homogeneous, labor and capital, even we start questioning the assumptions, right? But still, as we said, these are nice models, these are nice stuff to start with, right? So we should learn them. So, but basically this is the case. Now coming back to the problem that we have solved in the exam. So if the production function is homothetic, can any of these inputs be inferior? Right? So they cannot be inferior, because if it's homothetic, you know that it should be like this. So when you want to grow, you should always use more capital and more labor. This is what it says, right? But like in the homothetic case, because it would be a line. But if one of them is inferior, then it has to, this expansion path should go at some point backwards, right? So it cannot be a ray that is going through the origin, okay? So it should be like a weird curve. It could be, right? That's why in the beginning I drew the expansion path as this wiggly line, because we don't know. Only if it's homothetic production function, then I know that it's a line, okay? So this is basically the case, all right? So just keep this in your mind. If you have something like this, then your labor would be an inferior input, okay? Now, remember, once we have these, so we actually understood what is lambda. So we actually understood the expansion path this time. So when I tell you, find me the expansion path, then you'll be solving the cost minimization problem and then getting the, right, from the first two conditions, you would be getting the expansion path, right, from here, from these two guys, right? So basically it would be from here. And then, but remember, we minimize this total cost function. So don't get confused that this is not a constraint. So this is actually the value of this will be determined later, right? You'll find it by finding L and K. But the value of this is determined to begin with, okay? So if you don't want to get confused, I can write it like this. So this is my objective function, okay? But we call it cost function, total cost function, the optimal, when we put the optimal values back in there, okay? And this is the constraint because it literally binds us, right? So it literally constrains us. So basically, we have this. So when we solve this problem, we said that we're going to get, from here, we're going to get the optimal amount of, so minimize wage times L, R times K, LK, okay? So this is basically subject to, we said F of LK, which is equal to Q0. When I solve this problem, I'm going to get my LC, which is and KC, we call them conditional input demands, right? So these are functions of what? LC is a function of WR Q0, right? WR Q0. And when I plug these guys back into my objective function, I get my value function, and I called it either total cost or cost. Cost, wage, R, Q0, okay? Or if you want, you can call it Q, whatever, okay? So this is going to be wage times LC, wage R, Q, plus R times KC, wage R, Q, okay? Now we're going to have, probably you remember from your introductory econ courses, this is called the total cost function, okay? Or cost function. Total cost function. Now I'm going to define average cost, okay? So let's define this. So we would have the average cost function. Basically, it's going to be cost function, wage RQ, divided by Q. So for 1 unit of output, what is your average cost, okay? On average, right, total cost per unit of output, basically. So this is the average cost function. We're going to have the marginal cost. So we can call it average cost, wage, R, and Q, again, okay? So you can have it. So the marginal cost function, what is marginal cost? MC, wage, R, Q, let's call it. So what is the marginal cost? What's marginal cost? It's the derivative of the total cost function with respect to wage R, Q, right? Marginal cost means if I would like to produce 1 more unit of output, how much will it cost extra, right? How much, so what would be the contribution to the total cost, okay? So basically, this is the marginal cost function, okay? Now, let's have this. I'll ask you this question. So let's see. I'm going to, so let me draw you some total cost functions, okay? So you see the link between, but through here, you see the link between, right? You see production function appears in this cost minimization problem. That's why, of course, it's going to affect the cost function, okay? Now you'll see, I'll ask you one thing. let's see whether you'll be able to figure this out. Suppose I have a total cost function like this. So let's say examples. Okay? Suppose my total cost function is like this. I put here total cost, I put here Q. I have one like this. And then let me have this. Okay, so let's have, I'm going to have average cost, marginal cost, and Q. Okay, fine. Now, so this is, in this case, I'm going to have, so what is this? If I have a total cost function like this, how can I write this total cost? So if I want to write this as a function, right? So total cost, obviously it's a function of Q, right? Suppose I was given wage and R. This is, right, sometimes, let's say, right, a constant times, as you say, hocam, A times Q, right? So in this case, what is average cost and what is marginal cost? Average A, marginal cost is also A, right? So these guys are like this. Average cost, let's say, marginal cost, which is, as you said, hocam, it's A. So this total cost function is coming from which production function? Do you have a guess? Guess. Yeah, so the easiest one is which one? You were saying it. So the easiest one? No, don't think of Cobb-Douglas. Yeah, let me tell you. Constant return scale, increasing return scale, or decreasing return? Constant return. But just think why. Okay, we'll cover this on Friday, but just think why it's if the production function, you see that there is this link. If the production function shows constant returns to scale, and when you solve this problem, apparently the resulting total cost function is of that form, okay? When you are given wage and R, okay? Just think for Friday.